All right, section 2.6, we're taking a look at related rates. So related rates is going to be all application problems. So the problems do tend to take a little longer. You'll notice inside of both WebAssign and inside of the written homework, there's not as many of them assigned to sort of balance that out. But do plan on this taking some thinking. So it's one of those catch-22s when a student says, when am I going to use this in real life? Or how is this ever used in real life? Because you want to know, because in your mind you think, it's really not important to be able to do X, Y, Z, whatever it is. But then when I tell you how to use it, you really didn't want to know, right? Because it's hard. It's applications. It's like real life application stuff. And I don't necessarily mean real life to your specific life, but it's how it's used in real life, okay? So related rates is one of those application areas. So some guidelines for related rate problems. So sometimes you'll make a simple sketch if it's appropriate, right? If there's a geometric image that's coming up in the description. Often there is, though not always. The second thing is to set up an equation relating the relevant quantities. So if your image looks like a square and you're talking about area, you're going to set up an equation that relates area to length and width, whatever the geometric shape is or the things that are being compared. Number 3, we're going to differentiate implicitly. Okay, so we have done implicit differentiation, but not in this way. So you'll see what that looks like for implicit differentiation. Do you remember when we had like the X's and Y's that were so embedded inside of each other where we couldn't really separate them very well? And so we had like dy dx's showing up in the middle of the problem. That was implicit differentiation. So it will have that nuance to it, but there's a difference to it as well. The difference is that we're going to implicitly differentiate both sides of the equation with respect to time, not with respect to x. So we always had dy dx's showing up, right? So we're going to have dy dt, dx dt, dr dt, dA dt. It's always going to be with respect to time. The fourth one is we're going to substitute in values for known quantities and known derivative quantities. And the last thing is to solve for the remaining rate. Okay, so as you're sort of keeping track, these are the 5 steps. I'm not going to label them as we go, but we are going to think back to where are we in this process as we go through this. All right, so here's an example. We were at the lake this weekend. Nobody fished. It's too cold for that, in my opinion. But this is a fishing example nonetheless. A fish is reeled in at a rate of 1 foot per second from a point 10 feet above water. So imagine the person is standing on a dock or a person is standing on a boat. At what rate is the angle of elevation, you may or may not remember what that is, I'll show you, between the line and the water changing when there's a total of 25 feet of line from the end of the rod to the water. So as we're taking a look back at these guidelines, a sketch is definitely appropriate, right? Okay, so you can make your sketch more detailed, but we've got our guy or girl, whoever, and they're fishing. And their fishing line is going from them out into the water, somewhere over here, and here's my water. Do you see a shape forming? It is, it's a triangle. So there is a triangle shape that's forming here. I'm going to try and make mine look triangular. It's not going to be perfect, but you imagine here. Here's my triangle forming. This is the water at the bottom. They're standing up on the boat or on the dock or whatever, plus they've got their height of their pole above where their feet are standing as well. Okay, so we've got our triangle. Angle of elevation, it says between the fishing line. So this is the line, right? And it's taut. If they're reeling a fish in, it is a straight line. It's not, floppy out there. It's not the way it works. And it talks about the water. So here's our water down here. So the angle of elevation is right here that it's describing. The angle formed between the water and the fishing line. Does that make sense? Okay. Now, there's a few things that we have. We have the 3 sides of the triangle. We're just going to label all of them, and you can label them whatever you'd like. I'm going to label this one Y because it's a vertical distance, and I'm going to label this one X. And I'm going to label this one over here, I don't know, we'll call it C, like for hypotenuse of a triangle. A, B, C, X, Y, Z, do whatever you want, doesn't matter. But give it a letter. Now, it says that we are going to be pulling our fish in. So what's actually changing is the fishing line's location, right? So eventually the fishing line will be like right here. Because as they reel it in, what actually happens is that the fishing line gets shorter, which means the distance between the person and the fish is getting shorter, right? Or the person in the waters, the line, the length of the line between the person and the water. That piece is getting shorter. So what's actually changing is this length right here. This theta is changing, right? It's becoming larger as the fish gets closer to the boat or to the person. And this length right here, x at the bottom, is changing. But notice y does not change. Okay? So there's going to be some pieces in your problem that will be constant, they're never changing, and some pieces that are going to be shifting as we go. In this particular problem, most of it's changing, but y is not. Okay, so we are at the point where it asks us to find the rate. I've got one more piece of information I didn't write down yet. It says that the fish is reeled in at a rate of 1 foot per second from the point 10 feet above the water. Oh, so it tells us this right here is 10. We can actually change our y to say 10 because it's constant, it's never changing like we talked about. And it might be good for you to write that down, that it's constant. I know it also tells you that the fishing line is 25, but it's only 25 at one point in time, right? It's still changing. And we're going to use that 25 in a moment, but we can't put 25 in for C right away because it's not always 25. But y is always 10. Okay, does that make sense? Because that's a really big important piece that people miss all the time, is which numbers go in immediately and which ones have to be have to be added in at the end. Wait on them, okay? All right, so taking a look at this triangle, let me erase this piece where I moved it before. Taking a look at this triangle, the relationship that we're wanting to describe between what is changing is the fishing line, the angle theta, and this angle, or this line x at the bottom. So what quantity relates C, theta, and x? Which one? Okay, so sine, cotangent, it's some trig identity, right? There's some trig identity that relates the theta to these two sides of the triangle. So this side of the triangle, right, well, this side of the triangle is the hypotenuse up here. What's the side at the bottom? Is it the opposite or is it the adjacent? It's adjacent. It's touching my angle theta. So there are three basic trig functions that we're going to go to. We're either going to go to tangent, sine, or cosine. Which of those three, did you guys learn SOHCAHTOA like in geometry? Okay, so what's that? Yeah, okay, so it's cosine, right? So if you don't remember, it's been a minute or two. Sine is the opposite over the hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. The one that we're using here is going to be cosine. It's the adjacent over the hypotenuse. Those are the quantities that are adjusting. And we can set up a couple of things. Actually, let me write them both down because I probably should clarify that. So the cosine is the adjacent, which we don't know, which I called x, right? Over the hypotenuse, which is, all my letters on my paper are not what I put on my screen. I should have watched for that. Over C. We can also set up a relationship for sine. The sine of my angle theta would be the opposite. What is the opposite? It's the 10 over the hypotenuse, which is C. I really shouldn't have done that. Okay. And what we're wanting to do is we're wanting to take the derivative as the things change. Now, the one that's the easiest to take the derivative of is the one that actually has the fewest variables in it. Does that make sense? So while these relationships, and I could set up a tangent relationship as well. There would be nothing wrong with me writing that down. I could write down that tangent, I'll just write it here. Tangent of theta is opposite, which is 10 over the hypotenuse, or over the adjacent, which is x. I could do that as well. But the one that I want needs to include C, first of all, because I know C is 25 eventually, right? So I don't want the tangent one because it doesn't even include the C equal to 25. I need to use C equal to 25. And it's preferable to use the sine one because the 10 is constant and it's not changing. And I'm never going to know, I mean, I am eventually going to know where I could figure it out, but I don't have it given what the value for x is, right? X will change and it will keep changing depending on what the 25 one, the length of the line, the C is. So the one we're actually going to end up using is the sine one, not the cosine one, because it only has one unknown side as opposed to having two unknown sides. Does that make sense? Okay. So what we want to do is we want to implicitly differentiate. So let me rewrite this in a way that's more helpful. This is sine of theta equals 10c to the negative 1. Is that okay so far? Okay. And we're going to take the derivative. Okay, so you guys know what the derivative of sine is. What's the derivative of sine? Cosine. So the derivative of sine of theta is cosine of theta, but then the derivative of theta is going to be d theta dt. That's the implicit differentiation part. And the reason that's happening is that the theta is also changing with respect to time. So it's a variable quantity, right? It's adjusting, it's changing, so I have to multiply it by its derivative. The derivative of theta is d theta with respect to time dt. On the other side, 10, that's good. What's the derivative of c to the negative 1? Good, negative 10c to the negative 2. But c is changing, right? That's the fishing line. It's changing with respect to time. So I have dc dt. Okay, everybody good so far? Very good. Now, some of these things we know. I underlined it above, and then I never identified which piece it was. I shouldn't have done that. Up here it tells us that the fishing line is reeled in at a rate of 1 foot per second from the point. That's a rate, right? Foot per second, that's a rate. What is that a rate that's changing? Is it x, is it y, is it theta, or is it c? What is it relating to? C. Because it says fishing line, and the fishing line is what we called c, right? So this is talking about dc dt. And it's bringing it in, which means it's actually a negative 1 feet per second. Does everybody get why it's negative? Okay, it's getting shorter. Okay, the fishing line's coming in. If the fish were pulling it away, it could be getting longer. Right? You could change the problem a little bit so it would be positive. So what is that telling us over here? Well, right now, what is it asking for? I didn't highlight that. Let's go back to get that first. It wants us to know at what rate the angle of elevation theta between the line and the water is changing. So it's wanting to know the rate of what?
The d theta dt.
Yeah, it's asking us to find d theta dt. Okay, so that's the question it's asking us to find. So the unknown quantity, here in a minute, the only one that's going to stay unknown is the d theta dt. We actually know c. C is 25. At the given point in time we're talking about, c is 25, so that's 25 squared as the denominator. And dc dt is negative 1. But I got a problem. What's my problem?
You don't know what theta is?
I don't know what theta is, right? It was not given to me in the problem. It's an unknown quantity, but I needed to do the problem with the theta in it. All of the relationships had theta in it, and I'm asked to find d theta dt. So I've got to be able to figure out what theta is. Any idea how I might be able to figure out what theta is? Actually,
you could do sine equals 10 over 20.
Okay, so say that again louder. Alyssa, louder.
So you could set sine theta equals 10 over 25. And then,
Okay, so we had a relationship that the sine of theta was equal to 10 over c, right? And at the point we're looking at, c is 25. Everybody good? So if I put this in at this given point in time, this would be the angle theta in the image that I've got right now. So how would I figure out what theta is? Do you remember?
the sine to the negative 1.
Yeah. So we will do the inverse sine. Let me space. Of both sides. So the inverse sine of 10 over 25. So these cancel, leaving me with theta.
Over 25 squared?
Nope, just 25. Yeah, I'm using the relationship right here, not the derivative relationship. It's not about the derivative, it's about the actual relationship between the sides, like SOHCAHTOA. Yep, thank you for asking. So inverse sine of 10 over 25. Do you have a calculator? You'll need one. In radians, remember. Getting 0.4. We'll keep like 4 decimals for right now, just so that we don't lose any accuracy along the way. Did anybody else get that?
Yeah.
Yeah? Okay. I like confirmation. It's good. So over here, my cosine value, or I'm sorry, not my cosine value, my angle value inside of cosine is 0.4115, like that. And at this point, everything has a quantity value, right? There's a numerical value except for the d theta dt, which is exactly what it said I was supposed to be finding. So I can find the cosine of 0.4115. That's 0.9165. I still have my d theta dt. On the other side, I do have 2 negatives, so this is going to cancel to be positive. I have 10 divided by 25 squared, which is 0.016. And then I would divide that by the 9165. 9165. And it's a very small value. Did you get a very small value? Okay, that might be a little too tiny. I have 0.0, where'd my paper go? 175. That's the numerical quantity. I do need units. The very cool thing, we talked about it before, about this notation for derivatives, is that it tells you how the units are going to be. Theta is going to be whatever the units of theta are on top. T is going to be whatever the units for time are on bottom. So my theta will always be in radians, right? Because in calculus we're working with radians always. And then what's my time in this problem?
Seconds.
It's seconds. So the units here are radians per second. As you're doing this, I know WebAssign can be pretty persnickety about its decimals. So if you're feeling like you've done everything right and it's still fussing at you, telling you your answer is wrong, what you might need to go back and do is go and write your decimals out further. So if you've chosen to truncate them and only use 2 decimal places, that's probably going to be a problem in general. 4 decimal places might not even be enough. You might need to use 5 or 6 just to be sure that you're getting enough decimals to not adjust any of the values incorrectly. Does that make sense? Okay, we have one more problem I need to take a look at, I think. No, there's 2. Well, we're going to do one of them and I'll post the other one for you, because we're running out of time from that test. This one's a good one. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 30 centimeters? So let me make one overarching comment right now. I think that you should know formulas for sine, cosine, and tangent, opposite over adjacent, all that kind of stuff. I think you should know some basic formulas. I would not probably put this particular shape in the category of basic formulas you might have memorized and be able to recall at any point. So if I were doing this problem on a test, I would give you the equation that you would need to use. What shape is this? It's a sphere, right? Circles you should know, right? Like you should know area and circumference of circles. Those are basic shapes we use a lot. But 3D shapes are not ones that we use all that frequently. This is a sphere. So as we're taking a look at this, we'll start with drawing our sphere. There's the center. It references the radius. And it tells us a few things. So it tells us that the rate of the inflation rate, there we go, the rate of the gas going in is 800 cubic centimeters per minute. So this is 800 cubic centimeters, looks like this, per minute. What is this referencing? What quantity?
Volume.
It's volume, right? Cubic quantity is a volume quantity. So this is referencing how the volume is changing with respect to time. Does that make sense? Right? Cubic is always about volume. Well, that means we must need to know the volume of a cube. Do any of you happen to know the volume of the cube? A sphere, I'm sorry, I didn't know why I said cube. We were talking about cubic units. Yes, thank you. The volume of a sphere.
4/3 pi r squared.
You're really close. Cubed. 4/3 pi r cubed. Right? So if you're all of a sudden thinking, like, how did she know that? She's just amazing. She just knew it, right? I would give you that. So that's not one that I would expect you to use. Cubic quantities are not something that we tend to use all that frequently, okay? So if we were looking at this particular problem, I would tell you that the volume is equal to 4/3 pi r cubed. Okay, and the volume is obviously changing, right? And the other thing that's changing is the radius, right? If the volume changes the balloon, the radius changes the balloon, right? Until it pops, then we got a problem. But that's how it works. If the volume decreases, the radius also decreases. These things go in correspondence, and they go in correspondence. This is the equation that's used, right? The volume equation. But we want to see how they're changing with respect to their quantities adjusting, not just how they are related to one another. So we have a derivative to find, right? Each time we're looking at this, we're finding derivatives. Well, what is the derivative of volume with respect to time? dv dt. So this one's actually much nicer than the previous problem in the sense that the variables are separated on either side. There's not a variable inside of another, like the trig function, right? We had the sign of the variable, right? Or cosine or whatever we had. So this is very nice. It's just dv dt. I don't have a v left in my problem like I had a theta left in the last problem. How about the other side? Derivative of 4/3 pi r cubed. 4 pi r squared. Does anybody recognize that formula? I know I'm not quite done. It is 4 times the area of a circle. It's actually the surface area of the sphere. So I will leave that to Dr. Drake next semester for those of you who have Calc 2 to explore all the beautiful quantities. But there's a relationship between volume and surface area, and it has to do with derivatives. And we just saw one, right? Isn't that cool? I'm missing something. I need dr dt, right? The rate is changing with respect to time. The rate is also a variable quantity. So I have dr dt. In particular, any variable I have in the problem is going to have a d of that variable dt every single time for a related rates problem. Now, let's see. dv dt they gave me 800. The radius they gave me 30. So the only thing that I don't know, which is what I'm actually also asked to find, is dr dt. Right? Yeah. It says, how fast is the radius of the balloon increasing? That's a rate. So that's the part I'm looking for. So this one is 800. If you want to write in the units as you go, you can. You don't need to. For my benefit, you're going to have to put the units on at the end. If it helps you to keep track of them as you go, go for it. If it confuses you and it makes a mess of it, because that's kind of how I feel about it, then just leave them off till the end. This is 4 pi. My r is 30, so 30 squared. And then dr dt. So let's see. I'm going to do 4 times pi times 30 squared. It's a very big number. So I have 800 on the left. I have 11,000. I guess it's not that big. 309.7336 equals, or not equals, sorry, dr dt. And then we would divide by the 11,309. 7336. And these are often asked in terms of 4 decimals, so that's what you'll see me doing most of the time. I find that dr dt is equal to 0.0707. And then I need units, because I left my units out in the middle. The units on the radius are centimeters, and the units on time in this problem are minutes. Back over here, minutes. So this is centimeters per minute. Does that make sense? Okay, let me get the picture set up on the next one, and then I'll push pause just like I've done before and record the last bit after y'all leave so you can come back and finish it. Our last description is a very interesting one because we imagine it being a two-dimensional object, but it isn't. Oil spills out of a tanker at a rate of 90 gallons per minute. The oil spreads out in a circle, but the circle is thick because oil is not like water, right? It doesn't just dissipate until it's flat. Agreed? It's going to stay kind of pooling. And so it's a circle with a thickness. What shape is that? It's a cylinder. So I'm going to draw an exaggerated looking cylinder just because it's easier to look at, but I have a very, very, shallow cylinder for this image. So I have my circle, very thin, off my screen, and then it's going to come down and create a cylinder below. Does that make sense to everybody? That I've got a cylinder I'm looking at approximately, at least that's my best image that I can work with. It's talking about the volume. It says that the oil spills out a specific rate. This rate of 90 gallons per minute actually has a ratio conversion. And I'll do that when I do the video later. But I want to get the part that's more related to what we've already been looking at. But it's all about the volume of this oil. And the volume for a cylinder, do you remember that one? That one's a little bit more familiar, maybe. Yeah, pi r squared, right? It's the circle's area times the height. I didn't get the squared in there. Sorry, pi r squared times the height. So my volume is pi r squared times the height. The thing that's tricky about this is that the height is constant, right? But the radius is changing. So this is kind of like that first problem I did where the height above him being above the water was constant, but the fishing line and the lower piece were changing. So on this one, my volume will stay the same as V right now. And my height is a given constant of, 1/8 of an inch. Now we're going to have to consolidate and fix some issues in a minute. And the issues we're going to have to deal with is the fact that this is 1/8 of an inch, and we're going to have a very widespread oil spill because it's talking about it in 100 feet. So you're going to have to, and what I will probably be doing here in a moment is changing my feet into inches. Okay? Before I do it, let's do our derivative and then I'll let you go. So what is the derivative of volume? dV dt. And then what is the derivative of pi r squared times 1/8? 2 pi r dr dt, right? The radius is changing as the oil spills out, the radius is increasing, and I still have my 1/8 of an inch thick out here. 1/8 is a constant, right? It doesn't go away. It's just multiplied by the result. Okay, so I'm going to push pause. I'm going to let you guys clear out, and then I'll finish this up after you leave. Okay, so like I mentioned earlier, we have our our radius at 100 feet, and we have our thickness at 1/8 of an inch. So we can either take the 1/8 of an inch and change it into feet, which will be a very small number, which is okay, and we can do that, or we can take our 100 feet and we can change it into inches, which will be a very large number. Either way, it doesn't really matter. I mentioned in class that I thought I'd probably just go ahead and with the feet, and I think I will. So my radius eventually here is going to be 100 feet. And we're going to do some dimensional analysis. 1 foot is equal to 12 inches. So if I multiply this, I'm going to get 1,200 inches. Now that's not terribly huge. If you change the inches into feet, you're going to get 0.0104 inches. That's not terribly small. The numbers that come out of this are going to be one or the other pretty easily. It might tell you in WebAssign which way to go. It might tell you that it wants your final answer in a specific quantity. If it doesn't, then it should allow you to do it in either one, and that's what I would allow on my papers that you're turning in class as well, either on your homework or your quiz or your tests, okay? So this one I'm going to use is going to be the 1,200 feet. I'm sorry, 1,200 inches. So up here, I have 2 pi. My radius r is 1,200. dr dt, it actually gives me some information about which one I'm finding. So let's take a look. it's talking about the oil spilling out at a rate of 90 gallons per minute. That's related to the volume. And it wants to determine the rate at which the radius is changing. So it's the drdt that I don't know. So I'm going to go ahead and write my 1/8 next to the 1200, and then drdt at the end, it's the quantity that's unknown. Now the dVdt they give me is actually very interesting. The dVdt they give me is in gallons per minute. Now that's fine because gallons is a volume quantity, but it's not especially helpful because I really would rather it be in inches or feet because I'm working with inches and feet in terms of the dimensions of my shape, right? So I really don't want it in gallons. So I'm going to give you a conversion that's very useful. Again, if I were using this particular problem on the test, I would give you this conversion. There's absolutely no reason that you would be expected to know this. But 1 cubic foot is actually equal to 7.5 gallons. Okay, so that's the conversion that I'm going to need. So I've got my gallons per minute, so I need to turn my gallons into feet. And then I'm going to need to turn my feet into inches, right? Because I decided, just a moment ago anyway, to work with inches instead of with feet. So my gallons are 90 gallons. I'm sorry, not 90 gallons, 7.5 gallons, the right number, to the 1 foot. And then I have 1 foot compared to my 12 inches, right? So if you haven't done dimensional analysis before, these are just 3 fractions that we're multiplying. Gallons cancel, feet cancel. That's how you know how to set them up in the right location, is so that they have them in the numerator and the denominator they're canceling. What I'll end up with here in a moment then is going to be inches on top and minutes on bottom, right? And I'm sorry, it's supposed to be, I did make a mistake. This is cubic feet. And so my cubic inches needs to be cubed as well. So this is cubic feet canceling. So I actually end up with 12 cubed. My apologies. The 12 has to be cubed in order to be into cubic inches. So I'm actually going to be multiplying 90 times 12 cubed divided by 7.5. This is the one where if I'd done it in feet, it would have been a much smaller quantity. Now I end up with 20,736 cubic inches per minute. So that's maybe not the most friendly value, but it could be worse. So we're going to do 20,736 on the left-hand side of the equation. So I've kind of got a mess going on. I apologize. Let me see if I can shrink this. Actually, let me do it that way. Just shift that over a little bit, and then we'll move this over. Cool. So we just need to calculate these individual pieces, multiplied together, and then divided over to the other side under the 20,736. All right, so 2 pi times my 1200 times my 1/8 on the right-hand side gives me 942.4778, and then I've got my drdt. Okay, and then I will divide my 20,736 by that quantity. I'm not going to write it out, but you know that I'm doing it. So 20,736 divided by 942.4778, and my drdt will be 22 point, and if I use 4 decimal places, it'd be 0016, and that units on that, right? The radius units that I chose to use were inches. So inches per the time units that they're using here, which is minutes. So inches per minute. If we had been working with feet, just so you know, we would actually get 1.8335 feet per minute. The rate would be quite different looking. So we want to make sure that we're sticking with one quantity or the other the entire way. In the end, on this one, we get inches per minute.